Hello everyone, welcome to another lesson. Today our learning objectives are to analyze and sketch graphs of functions. The steps that we will take in general, first of all, we want to determine the domain of the function. 2, we want to locate the x-intercepts and the y-intercepts. 3, we want to determine the end behavior, that is, we want to find the limits as x approaches positive infinity and negative infinity of the function. In these cases, we will also be finding your horizontal asymptotes. 4, we want to determine if f has any vertical asymptotes. And then we want to calculate f prime of x as the first derivative. Find the critical points and determine the intervals where the function is increasing or decreasing. And determine whether f has a local maxima or minimum. And 6, we determine the intervals where f of x is concave up or concave down. You find f double prime of x. When you do that, you can set equal to 0 or where it's undefined. That's where you find your points of inflection. You could also use the second derivative test to determine whether or not the critical points are local maxima or minima, right? That's where you use the second derivative test to check. Okie dokie. An example. Analyze a graph of f of x is equal to 2 times x squared minus 9 over x squared minus 4 by computing the following. Then sketch the curve. So you want to compute the x-intercept. This should be the y-intercept, the horizontal asymptote, vertical asymptotes, critical points, inflection points, maximum and the minimum points. And determine whether the function or where or what intervals the function is concave up or concave down. For part A, your x-intercepts would be -3, 0. We find our x-intercepts by setting y is equal to 0 and solving for x. And likewise for your y-intercept, you set x equals 0 and solve for y. So your y-intercept is 0, 9/2. For our horizontal asymptotes, we want to find the limits as the function approaches positive infinity or negative infinity. And in those two cases, if we used our algebra that we learned about rational functions and divided by the highest exponent of x, we end up with 2 as our horizontal asymptotes in both cases. Your vertical asymptotes would be where your denominator equals 0. Set your denominator equals 0 and solving for x. We have x equals -2 and +2. Your critical points would be where you set your derivative. First derivative equals 0, and here you will have for your numerator, x will be equal to 0. For your denominator, you get the same things that you got for your vertical asymptotes, which was -2 and +2. And we already said those were asymptotes. So our critical function point that we'll focus on to check max or min will be at x equals 0. Inflection points, you take the derivative of the first derivative and you end up with -20. After you've simplified 3x squared plus 4 over x squared minus 4 cubed. Again, this is undefined at x equals -2 and +2, and then these were your same vertical asymptotes. From the numerator, it just wouldn't make any sense, so there's nothing that you can, in terms of real numbers, you wouldn't get any answers there. Then you want to test to find your maximum or minimum, test the critical point f of 0. You find that you have a negative over negative, that's a positive number. It's concave up, therefore it's a minimum point. And then to find your concavity in other areas, use these intervals, -infinity to -2, -2, 0, 0 to 2, and 2 to infinity. Of course, using if we're just focusing on our second derivative test, we could have just do -2 to +2 here. And we already tested a point in that interval. Your 0, and we found that it was concave up. So typically everything in this place would be concave up as well, but we can still go ahead and test these intervals to double check these and see what happens. So we choose test points x equals -3, -1, 1, and 3, and then take your second derivative there in these places. And so if you take the second derivative of -3, you find that we get a negative number, so it's concave down. And as noted, the f double prime of -1 will be positive, so it's concave up. F double prime at 1 will be positive, so it's concave up. And f double prime at 3 be negative, so it's concave down. So that concludes our interpretation of it. Now, if you want to sketch the graph of this function, let's do a quick sketch of it. So let's say we had, let's kick in our intervals here. That's -infinity, +infinity, and here's 0. And then we said we had vertical asymptotes at +2 and -2, and we had a minimum at 0, 9/2, so it's going to be going up in that direction. It's also concave up, so that also takes care of our intervals that we had here. And then on this side, it's concave down. It's concave down on these parts, right? So where did we have we had a horizontal asymptote at 2. We had a horizontal asymptote at 2, so we want to draw that in as well. We had a horizontal asymptote at 2. So here we go, y equal 2. That's horizontal asymptote. So then we can fill in our other parts. Now it's concave down. Graph is concave down here and concave down in this section as well. So that completes what our graph would look like. We want a sketch of a graph of the function having the following properties. The domain is -infinity to +infinity. Y equal 3 is a horizontal asymptote. The limit as x approaches -3 of f of x is equal to 2. The f of -3 equals 1. The limit of f of x approaches 1 from the left of f of x is equal to +infinity. The limit as x approaches 1 from the right is equal to 2. The limit as x approaches infinity of f of x is equal to -1. So we have to take all these into consideration to sketch the graph. So we want to take all these things into consideration. So y equals +3 is a horizontal asymptote. It didn't say whether it's from the left or from the right, but we draw in the line y equals +3 right here. Okay. Then we know the limit as x approaches -3 equals to the limit of f of x as x approaches -3 equals 2. So if we are approaching -3, right, so let's fix this. So limit of f of x. So we need to put in that 2 right there. Let's put in that 2. Fix this up a little bit. Let's fix that up a little bit. So then we have that 2. So we gotta like squeeze this up a little bit to where it's 2. So it's approaching. You know the function value is at 1, but it's approaching at 2. Right? So you have to have an open interval right here. And then the f of -3 equals 1, so that takes care of it. Here's a point -3, 1, point -3, 1. You want to have that point there. Then the limit as x approaches 1 from the left is positive infinity, and approaching 1 from the right, that is equal to 2. So this here x equals 1. And also the limit as x approaches positive infinity, so that's a y equals -1 right here. So this is what one graph of it would look like. It's what a graph of this could possibly look like. Okay, all right. If you wanted to bring this through and go all the way up and then come back down to, just get into the line y equals 3. If you want to crisscross a little bit, that's fine. But as long as it's tending towards that line as we go to -infinity, and it's approaching the line y equals -1 as we go to positive infinity. So there's a possible solution right there. Following is a graph of a derivative function, f prime. So this is your f prime function or your derivative function. We want to use the graph of this function to identify intervals on which f is increasing, on which f is decreasing. Use the graph to identify a relative maximum of f. Use the graph to identify a relative minimum of f. If you look at this graph, you can identify a number of intervals. If you want to separate them, you can possibly do that. And by these red lines, from -infinity to 0, and from 0 to whatever this number is, maybe about 3. And then from 3 to 5, 3 to 6 rather, so that's about 6. 0, 3, that's 6, and then positive infinity. So you can sort of demarcate it, right? And then identify the areas where your derivative function is positive and your derivative function is negative. So your derivative function is positive up here, derivative function is negative down below the x-axis. So wherever it is positive, that means you can conclude that it's increasing, and that the original function is increasing. Wherever it's negative, that means that the original function is decreasing. So that's some analysis you can do right here. Okay, so intervals on which the function is increasing would be in this interval right here and right there, okay? Because it's where it's above the x-axis, so that would be -infinity to 0, and or you could write union 6 to infinity, right? So it's increasing on those intervals, -infinity to 0 and 6 to infinity. And then where it's decreasing would be from 0 to 6, decreasing from 0 to 6. Okay, and then where it is a maximum value, it's going from increasing to decreasing. That's a maximum value, so that's x equals 0. X equals 0. Because it's going from increasing to decreasing. And then that's x equals 6. That's where it's moving from decreasing to increasing. So that's our answers. Thanks so very much for watching, and like, subscribe. See you next lesson.